So far, we've analyzed Hooke's law as the force due to a spring equal to the opposite of the spring constant K times the displacement X. In a given system, if I have a spring like this, we would define its elasticity as K, which is a standard value of elasticity called the spring constant. And the spring constant is measured as newtons per meter, basically describing the proportionality constant of how much force the spring applies based on the displacement that occurs. And the negative sign, of course, is just the fact that the force is in the opposite direction of the displacement. And a simple example we've already studied is if I take if I take a spring with some known spring constant and I add a mass m to the spring in a vertical system with it attached to the ceiling at the top, then this thing stretches out some displacement x. The force applied by the spring would be in the opposite direction of that displacement, right? The x and fs are always in the opposite direction because a spring tries to return to its equilibrium position. Of course, we know in this particular situation that we can determine the force of the spring based on the mass f of g hanging down here off of the end. If the system is at equilibrium, then the forces are balanced. We can identify the magnitude of fs as f of g and then solve backwards for k based on the displacement. This is a pretty simple activity applying Hooke's law, and this is useful when looking at singular elastic systems, whether or not it's a spring or a cable or a rubber band or anything that has some known or measurable elasticity. But what can be interesting is to look at a complex spring system. And I use the word complex when I think about complex DC circuits. Complex DC circuits are circuits that combine both resistors in series and parallel combinations. In order to describe complex spring systems, we'd like to start with the simple combination of series and parallel connected springs. So if I take and I analyze the series connection first. This would be a description based on space. I'm going to do it horizontally rather than vertically. But if I think about attaching a spring directly in line with a secondary spring and then applying some known F applied out here on the end in order to stretch the system out, right? If I fix this end to the wall and I attach the two springs to one another, where I have K1 here and K2 here, where not necessarily these two springs are the same elasticity, although they could be. The question is, what is the equivalent elasticity of this system by connecting two springs in series? In order to answer this question, I need to think about the fact that when I stretch this, by applying Fa on the end, this spring is going to stretch out some displacement from its original position. Let's mark that as being here to there. And so we have this small change, x1, for the first spring. But then we also have a secondary change from here to there, x2, for the second spring. Now it's true that these may be the same, but it's also true that they could be different based on the elasticity values of the given spring. And so they may stretch unevenly. And so this becomes a little bit even more tricky to conceptualize. And so the best approach really is to go back to our Hooke's law and analyze the situation accordingly. And so we would describe the overall force, the equivalent force of the spring, as being the equivalent spring constant times the equivalent displacement. Now, if we think about the overall displacement of the system, where Fa was applied to where Fa is now applied, then that is pretty obvious that x equivalent is the sum of x1 plus x2. In order to come up with an analysis of the overall elasticity, then, what we're going to do is we're going to introduce this into our equation here and see if we can come up with a relationship for the overall elasticity. And so what we're going to say is that x1 can be described as f1 divided by k1. And then, of course, x2 can be equal to f2 divided by k2, where this would be the force applied just to the first spring, and this would be the force applied just to the second spring. Now remember that the equivalent displacement is these two terms added together. So we can rewrite this first by solving this for the equivalent displacement. So I can say that xeq is equal to fs divided by k equivalent. Now I'm dropping the negative sign for now because it's irrelevant in terms of the relationship that we're going to analyze, but there would be a negative sign carried through. But for argument's sake, let's just leave it like this. So if we expand our equivalent displacement out as these two functions, right, then we can see here that f1 over k1 plus f2 over k2 is equal to fs over k equivalent. Now, what we need to remember is that when we are pulling, the system is at equilibrium, which means that the force with which this spring is applying, F1, pulling back in its original position, is being pulled on by this spring, F2. And F2 is being applied as a resistant force to that system, F2 to FA, right? Which is what we're thinking of as being the overall spring force. And so what that means is that based on the fact that the system is at equilibrium, F1 is at equilibrium with F2, and F2 is at equilibrium with FA, and FA is at equilibrium with the overall spring force, Fs. So F1 equals F2 equals F2 equals FA equals the force of the spring system pulling in order to resist the deformation of the system. So in a surprising kind of analysis using Newton's third law, we see that F1 is equal to F2 is equal to Fs. And this is because the system's at equilibrium and all of the forces are equal and opposite throughout the pathway. So if we go back to that, then that means that these are all the same and they cancel out. This yields a result for the force of a spring in series combination as having a K equivalent that can be calculated through the relationship of 1 over K1 plus 1 over K2 equal to 1 over K equivalent. And so this is how we would calculate K equivalent. So another way to say that is that K equivalent is equal to the sum of 1 over K to the n, where n goes from 1 to however many there may be, and then that entire thing is inversed. So the inverse gives me the equivalent resistance of the sum of the inverses. If you'll notice, this is the series combination for the force of a spring as compared to the parallel combination of resistors that we saw in DC circuits. And so it's a similar analysis. Now, if we switch and consider a parallel, springs in parallel, then we're looking at a system where I've taken multiple springs and connected them to a system like this, where I have one large connection and these anchored across the top like this. So when the springs are in parallel, we have the combination of K1, K2, and K3 springs, all applying an overall Fs that would be the resistance to the displacement as this moves down. So we can describe the overall force of the spring as being a combination of F1 plus F2 plus F3. But now what we see is that if we expand out the formula here, we have K1 times X plus K2 times X plus K3 times X. Now remember, we're trying to find the equivalent spring constant, and Fs is equal to the equivalent spring constant times the equivalent displacement. But the reality is that if I pull on this object and displacement down to here, then from here to there is my displacement. And the displacement is the same for K1, K2, K3, and is ultimately X for the entire system. That's to say that the equivalent displacement is X, X, and X, or X1, X2, and X3, which is why I've omitted the subscripts. And so this cancels across the board in this scenario. And so what I end up here is that the equivalent spring constant is the sum K1 plus K2 plus K3. And so we see that in parallel, Fs in parallel yields a sum of the net spring constants for the system. So this can be summarized that the equivalent spring constant for springs in parallel is equal to the net sum from n equals 1 to however many springs there are of the individual spring constants for each individual spring.